This is Unit 4, Section 3. This is the first day of Section 3, textbook Section 5.5. We are now going to be talking about function operations. So a little background info, because we're going to be using this today, but we haven't really talked about it yet. If we have a number written to a power that's a fraction, then we can actually turn that into a radical, because the fraction, the top number is the power, but the bottom number is the root. So here we have a to the m over n, so that really means it's a to the m power with the n root. I could rewrite that as 1 over n for the root. And negative moves to the bottom. We're not going to really focus much on that. We're going to focus really here on the top. So power over root is the important part here. Power over root. So the bottom number always represents the root we're taking. The top number always represents the power we're raising it to. So we're going to rewrite each of these into radical form, and then we'll evaluate them without a calculator. So 16 to the 3/2. So I'm going to focus on the root first. So that means it's the second root of 16, or the square root of 16, and it's to the third power. So this is radical form. And now I'm going to evaluate it. So the square root of 16 is 4, and 4 to the third power is 64. All right, let's look at B. Power over root. So the fifth root, so we'll start there, of 32, and the power is 3, so to the third power. So the fifth root of 32 is 2, and 2 to the third power is 8. So you go ahead and try these, pause it, and then you can check your answer. All right, so let's check these. All right, number 1 is the square root of 4 raised to the 5th power, which is 32. Number 2, there was no number on top. It was just a 1, so there's power is 1. We don't have to write that. So it was just the square root of 9, which is 3. Number 3 was the 4th root of 81 raised to the 3rd power, which is 27. And number 4 was the 8th root of 1 raised to the 7th power, which is just 1. We could also do the reverse. We can rewrite it into exponent form. So here, my root is 2, and my power, the thing I'm raising it to, is just 1. So this is going to be 14 to the 1/2 exponent. For B, so my power is 1. It's not being raised to anything. And my root is 3. So that means it's going to be x to the 1/3 power. So you go ahead and try these, pause it, and you can check your answer. All right, so number 5 was 16 to the 1/4, and 6 was x to the 1/5. So now let's actually get into the lesson of function operations here, or operations on functions, really. So if I have two different functions, f and g, then a new function can be found by combining f and g in 4 different ways. I can add together the two functions, in which case it's just like adding together the two polynomials I would normally deal with. I could also subtract, the same as subtracting polynomials. I could multiply, which is the same as multiplying polynomials, and I can divide. What's going to be different now is the domains of the sum, difference, product, and quotients will consist of the x values that are in the domains of both of our original functions. In addition, when we're doing division, we have to exclude what would have made the denominator 0 as well. So let's look at our first example. We have f of x equals 5 times the square root of x, and g of x equals -8 times the square root of x. I want to find f plus g of x, and then I'll state the domain. So f plus g of x really means f of x plus g of x. So that's 5 radical x plus -8 radical x. So together, if I treat the radical x as my variable, then 5 plus -8 is -3 radical x. So f plus g of x equals -3 times the square root of x. The domain. The domain of f would be anything greater than 0, and the domain of g would be anything greater than 0, because we're not going to put a negative under the square root. So together, they're the same, so my domain overall is x is greater than or equal to 0, right? Or 0 to infinity. Now we'll evaluate f plus g of 16, which really just means I'm plugging in 16 for x here. So that's going to be negative 3 times the square root of 16. The square root of 16 is 4, so we get negative 12 for f of g of 16. Let's look at subtraction. I have these two big polynomials, and I want to find f minus g of x and state the domain. I could even do domain before I start. The domain of each of these polynomials is going to be all real numbers. There's no restrictions on what I'm allowed to put in. So the domain of f minus g of x is also going to be all real numbers, right? Or negative infinity to positive infinity. So now let's actually do this. Let's subtract. So we're going to get 2x to the third plus 4x squared minus 8x plus 4 minus all of this. So really, I'm going to subtract each of these things. Hold on, lost my pen again. Okay, so I'm going to subtract each of these things. So that's negative 3x to the third. Subtract negative 5x squared, so plus 5x squared minus 6x plus 9. So if I line it up like this, it's kind of easy to see that we're going to get negative x to the third plus 9x squared minus 14x plus 13. So that's f minus g of x. And now I want to evaluate it when x is negative 1. So if you recall, we could evaluate using synthetic, right? Synthetic was where we took all the coefficients. Nothing stopping us from doing it this way, putting negative 1 on the outside. Or we could plug negative 1 in for every x. I really do love synthetic, so I'm just going to do it that way. And we get 37. Right, I could have put it in here, so negative 1 to the third power is negative 1, times the negative is positive 1, negative 1 squared is 1, times 9 is 9, negative 14 times negative 1 is plus 14, and then plus 13. And that way also gives me 37, but I felt like that was quicker. All right, you go ahead and try this. You're going to find f minus g of x, state the domain, and then evaluate f minus g of negative 8. Pause it, and then you can check your answer. All right, so doing 6 times the cube root of 3 minus 2 times the cube root of 3, we get 4 times the cube root of, the cube root of x, not 3. Domain is all real numbers, because for cube roots, we're allowed to put negative numbers in. So all real numbers is our domain, and then when I substitute in negative 8 for x, I get 4 times negative 2, which is negative 8. All right, let's talk about multiplication and division. So here's where we're going to have to use what we did at the beginning of the lesson, because I have x squared and I have the square root of x. So when I'm doing fg of x, or f times g of x, I'm doing x squared times the square root of x. But really, I need these to be in the same format for me to actually do anything with them. So I'm going to change the square root of x into an exponent. So remember, power over root. The power of this was 1, and it's the square root, so the root is 2. So now I have x squared times x to the 1/2. And I know when I'm multiplying like variables, I add their exponents. So I'm going to do 2 plus 1/2. It might help to have a common denominator, so this could really be x to the 4/2, right? 2 is really 4/2, times x to the 1/2. So together, we have x to the 5/2. As for my domain, the domain of x squared is all real numbers, but the domain of the square root of x is just 0 or greater, right? No negatives. So that means overall, I have to limit it to the domain of the second one. X has to be greater than or equal to 0. or 0 to infinity. Even though I was allowed to put anything into x squared, this limits it. So now let's evaluate for f times g of 9. So that's x to the 5 halves is 9 to the 5 halves. So we could plug this actually into our calculator right now, or I could turn it into the root of 9 to the 5th power. So that's 3 to the 5th power, and that's 243. All right, this next one, f over g of x, f divided by g of x. So that means I'm going to take these two and I'm going to put them over each other, 4x over x to the 2/3. So I have to have them in, again, common denominator for the powers. So I'm going to have 4x to the 3/3, right? Because this is really to the 1 over x to the 2/3. And if you recall, when we divide, we're actually subtracting. So we're going to do 3/3 minus 2/3 and get 4x to the 1/3. So now, looking at both of the original functions, 4x, all real numbers, is my domain, and x to the 2/3. So my root was 3. And I'm allowed to put negatives in a root of 3. So that's fine. That would have been all real numbers as well. But now that it's division, I know I can't have the bottom equal 0. So what would make the bottom 0 would be x equals 0. So my domain is that x cannot equal 0. And now we're going to evaluate f over g of 27. So that's 4 times 27 to the 1/3, which is the same as saying 4 times the cube root of 27, which is 3. So it evaluates to 12. You go ahead and try this one, pause it, and then you can check your answer. All right, so we know that, again, this x to the 1st power is the same as saying x to the 5/5 power. So when I subtract 5/5 minus 1/5, I get 4/5. So 3 times x to the 4/5 would be my function. The domain, x can't be 0 based on the fact that x to the 1/5 is on the bottom. And then when I substitute it in, I get 48. Our last example here, we have from 2000 to 2010, the population in thousands of cities M and N can be modeled by, and they give us two different functions, and T is the number of years since 2000. So I want to find M minus N of T. So I'm going to line it up the same way I did the other one that was a big polynomial. I'm going to write out my first one. And now I'm going to subtract each of these. So I'm going to change all the signs and line it up underneath. So that's minus 2.5 t to the 3rd, minus 7.8 t squared, minus 0.41 t, minus 11.9. So altogether, we're going to get 0.8 t to the 3rd plus 4.3 t squared minus 1.06 t plus 3.9. And we want to know what m minus n of t represents. So if m was the population of city M and n was the population of city N, then by subtracting them, we're finding out how many more people live in M than N, right? We're finding the difference of them. So to say what it represents is how many more people live in M than N. All right, and you could say between 2000 and 2010 or whatever it is you like, but that's what it represents. The difference in the number of people that live between the cities, and M had more because it came first. So you're going to try this one. From 1990 to 2010, the numbers in millions of female and male employees from the ages of 16 to 19 in the U.S. can be modeled by these functions, where T is the number of years since 1990. So you're going to find f plus m of t and explain what that represents. You could pause and then check your answer. All right, so here we have our F plus M of T, and what it represents is the total number of male and female workers between 16 and 19. And that is our lesson for today.